So we begin by giving some definitions related to Fourier series, and then define what we call Fourier series of a function. Later on, we'll do some examples on how to calculate Fourier series of an arbitrary function f of x. And then before we start, just as a reminder, as I had initially told you, this course requires you to be very good at integration and differentiation. So please do some review on your integration techniques. Because once you define a Fourier series, most of the work, more than 90%, will be to carry out integration. So if your integration skills are okay, you are not going to have any troubles here. But if you have a problem on integration, please do some recap so that you are able to understand most of the computation that will be done in this chapter. So we start by defining a periodic function. So function f of t is said to be periodic of period t if f of t is the same as f of t plus t. Or we can use the argument x and say a function f of x So if a function f of x can be written as f of x plus t for a positive number t, then such a function is said to be periodic. This number t is called the period of the function. So the key thing in the definition of a periodic function is this relationship, that for any value of x, f of x equals to f of x plus t, and this t is always a positive number. So note that when you write f of x equals to f of x plus t, this will also be the same as f of x plus 2t. This is the same as f of x plus 3t. etc. Similarly, f of x equals to f of x minus t is the same as f of x minus 2t is the same as f of x minus 3t, etc. So we show that plus or minus 2t plus or minus 3t, etc. So a simple example for periodic function is a sine function and a cosine function. So examples of periodic functions include sine and cosine. So f of x equals to sine x is a periodic function because if you are to sketch the graph of sine, it will take this shape. So this is just as an example. So where this is 0, at this point we have 0, this minus pi, minus 2 pi, minus 3 pi. This is pi, 2 pi, 3 pi. This will be 4 pi. So from, for instance, 0 to 2 pi. So if I call this point A, this point B, this is a complete cycle. And then the graph repeats itself. So from this point, or even from this point here, from one crest to the next crest here, this is 2 pi. So remember, this will be pi, this will be pi over 2. This will be 2.5 pi. So the period of a sine function is 2 pi. So sine x can be written as sine of x plus 2 pi. So period is 2 pi. And then we have cos function. So we can sketch So roughly this is the graph of a cosine function. So this is 0. We have minus pi. We have pi, 2 pi. This is so 0, and then we have this is pi over pi is at this point here. It's pi over 2, half pi. And then here we have 2 pi minus pi. So this pi over 2. And this minus 2 pi. So also,
Excuse me, sir, we can't hear you.
okay, are you able now to hear me? Okay, sorry. Are you able to see my screen?
Yes.
Okay, good. So this is where we started from. So the first was to define a periodic function. And a function f of x is said to be periodic if a constant number t, f of x is always the same as f of x plus t for any given value of x in the domain of the function f. And if that is the case, the number t is called the period of the function. So the number t defines what we call the period of the function f of x. And then after defining the periodic function, we also see that you can do an extension that f of x equals to f of x plus t is the same as f of x plus 2t, which is the same as f of x plus 3t. The same values give f of x minus t, x minus t, and then f of x minus 2t, etc. And then we gave a few examples of periodic functions, the sine function and the cosine function. So both the sine function and cos function have period of 2 pi. So period simply the number of times we have a complete cycle, which happens after 2 pi steps. So I have the sketches of the cosine and sine function. So the next point was now to say that the integral of a periodic function does not change the value if the range of integration is equal to its period. So this is to say that if I integrate from a to b of a periodic function f of x with respect to x is the same as integral from a plus t to b plus t of the same function f of x dx. So whenever you are dealing with a periodic function, if the range of integration is equal to the period of the function, then the value of the integral doesn't change. So to our list of examples of periodic functions, also at the function y equals to a sine of omega t plus phi is periodic. What name do we give to this function from what we did in first year in applied math? Special name given to this?
Wave.
No, this is a wave, yes, but a wave defining which type of motion?
Simple harmonic motion.
Simple harmonic motion,
Yeah,
correct.
yeah.
Yeah. So this equation defines simple harmonic motion. This A defines the frequency, defines the amplitude. Then omega defines frequency. This phi is initial phase. Or simply the phase angle. This equation is actually this harmonic. So let's define orthogonal functions. So the system of finite functions phi naught of x, phi 1 of x, phi 2 of x, all the way up to phi n of x is called orthogonal. In the interval AB. If this is true, that the integral from A to B of any product of two functions in this set will always give you 0, provided that m is not equals to n, and the integral from a to b of phi m of x, phi n of x dx equals to m, which is a non-zero number, provided that m equals to n. So let's call this condition star. And then you can call this set of functions, call that equation 1. Call that, just give it a name 1. So if the value of the second integral in star is 1, that is to say that capital M equals to 1, then the system of function given in 1 is said to be normalized. So we can give some examples of trigonometric functions which are orthogonal. So the system is a orthogonal in the interval 0 to pi. So that means that if you take any two arbitrary functions in this given set, if they are different, they multiply them and you integrate from 0 to pi, you get 0. If it's the same function, then we should get a number m. If now we have sine x, sine 2x, sine 3x, all the way to sine nx, this set is also orthogonal in the interval 0 to pi. Another example of orthogonal functions. The system of functions sine of x, sine of 3x, sine of 5x, sine of 7x, up to sine of 2n plus 1x is orthogonal in the interval 0 to pi over 2. So the interval of definition matters. So when now you take odd multiples of x, you define by sine, then the interval becomes 0 to pi over 2, not pi, 0 to pi. Second last example. So the system of functions 1, cosine of pi x over L, cosine of 2 pi x over L, cosine of n pi x over L, and sine pi x over L, sine 2 pi x over L, all the way up to sine of n pi x over L. Now, following the first and second examples in A and B, this will be orthogonal in which interval? Zero to L. Similarly, the system of functions sine pi x over 2L, sine of 3 pi x over 2L, sine of 2n plus 1 pi x over 2L is orthogonal in the interval 0 to L. So then now let's define a Fourier series of a function f of x defined in the interval minus pi to pi. So let f of x be a single valued function So let us have a single valued function f of x defined in the interval minus pi to pi. Then the Fourier series of f of x is f of x equals to a naught divided by 2 plus summation n from 1 to infinity of a sub n cosine of nx plus b sub n sine of nx where a naught is given by 1 over pi integral from minus pi to pi f of x dx an is 1 over pi minus pi to pi f of x times cosine of n x dx. This for n equals to 1, 2, 3, 4, etc. And bn is 1 over pi integral minus pi to pi f of x times sine of nx dx. And then these constants a naught, an, bn are called Fourier coefficients or Fourier constants. So these are called Fourier coefficients or Fourier constants. So note that if you change the interval from 0 to 2 pi, if f of x is defined in the interval 0 to 2 pi, then the Fourier series will be given by f of x equals to a naught over 2 plus summation n from 1 to infinity an cos of n x plus bn sine of nx and then you define this as a naught to be 1 over pi 0 to 2 pi f of x dx an will be given by 1 over pi integral 0 to 2 pi f of x multiplied by cosine of nx dx. So here n starts from 1, 2, 3, etc. And bn is 1 over pi 0 to 2 pi f of x sine of nx dx. So n is 1, 2, 3, etc. So exactly the same thing, only the difference is the interval of integration. An exercise, skip one page to do this. So 1, state the Dirichlet's conditions for a Fourier series. And then number 2, state or give any at this point, I'm aware that you have also done other types of series in math courses, the Taylor series, the Maclaurin series. So what makes Fourier series a better series than, say, Taylor series and other types of series you've done before? So some useful formulas. So these formulas have been done before in other engineering courses, and they will be very useful when you are solving problems in this chapter. So what is the value of the integral from 0 to 2 pi of sine of n x dx? Please work out the value of the integral 0 to 2 pi sine of n x dx. Remember, n is an integer. So when you see all these values, n will mean an integer. So integral from 0 to 2 pi sine of nx dx. Don't disappoint your calculus teacher.
Negative n plus 2 pi n.
N? Okay, probably maybe
Negative 1.
it's not a very complicated expression. So maybe we can freshen up. Let's discuss together, and then probably the next one you'll be able to do on your own. So when you have to integrate, so this, like, the main question is, what is the integral of sine of n dx? So which integration technique do you apply?
Chain rule.
So substitution. So you'd say let u to be nx, so which means du is the same as n dx, which means dx is du over n. So this will be sine integral of sine of u dx is the same as du over n. So you pull out 1 over n to get 1 over n integral of sine of u du. And when you integrate a sine function, you get
Negative cos.
So this is the same as negative 1 over n cosine of u. So when we say integral 0 to 2 pi of sine nx dx with the same as negative 1 over n, and then cos of n x, because that's the value of u, and then x from 0 to x equals to 2 pi. So when you put in the upper limit, what do you get?
Cos of 2 pi n.
So so we have negative 1 over n into cos of 2 pi n, and then minus cosine of 0. So cosine of 0 is always
1.
Always 1. And then cos of 2 pi n. Gives? Remember, I've told you that this n is actually an integer, in most cases a positive integer. So when n is 1,
Oh,
cos
one.
of 2 pi,
One.
I'll always give you 1, okay? This will always be 1, this will always be 1. So 1 minus 1,
0.
0. So 0 by minus 1 over n. You get?
0.
Minus 1 over n by 0,
0.
0. So this will always give you 0. So the integral from 0 to 2 pi sine nx dx will always provide 0 as the final answer. And then number 2, please work out this. What if we have now cos of nx dx? Follow the same procedure and tell me the value of the integral.
Zero.
We get also 0. This will also give you 0. If you do the correct computation, then you must get 0 as the value of that integral. And then number 3, if you integrate from 0 to 2 pi of sine squared of nx dx, you'll get pi. You can always confirm this integral from 0 to 2 pi of cos squared nx dx also gives pi. Zero to 2 pi of sine nx times sine of mx dx will always give 0. Number 6, 0 to 2 pi of cosine of nx times cosine of mx dx gives 0. Integral from 0 to 2 pi of sine nx cosine of mx dx gives 0. H sine of n so this is not necessarily an integral, but just the sine of n pi is 0 and cosine of n pi will give you -1 power n. N is an integer. Number 10, sine of n pi over 2 will give you 0 when n is even, will give you 1 when n equals to 1, 5, 9, etc. -1 when n equals to 3, 7, 11, etc. -11 cos of n pi over 2 also has 3 values when n is odd, when n equals to 0, 4, 8, etc. And -1 when n equals to 2, 6, 10. Five minutes break.